So I'll just start off by giving a very quick intro to myself and Nethermind. So Nethermind is a somewhat Ethereum focused, but really, and L2, Ethereum and its L2 focused, but really not exclusive to that, crypto consultancy that started in 2017. We developed now what is now the second most popular Ethereum client, which is known as the Nethermind client after Geth. And then in about 2021, that's when I joined, we had what I call a Cambrian explosion of diversification. And basically Nethermind now does pretty much everything that you can imagine that's crypto related. It's like implementing clients, we have security, so there's formal verification, there's auditing, there's like monitoring services, we have like crypto economic, cryptographic research, consensus research, pretty much I'm going to stop this list now. I could continue on for a very long time, but basically if you have a crypto problem, we basically can probably solve it. But yeah, so my background is in formal methods, particularly for concurrency. As I said, I joined the company in 2021, and since then, we've sort of started focusing primarily on this sort of novel class of cryptographic protocols, which are known as zero-knowledge protocols. And as I said just right now, my expectation is really not that you know most of the words in this title. Really, most of this talk is context. There's actually basically, I'm going to say, kind of only one slide on the actual work that we did here. Most of it is like context of what is this, why should I be doing this, and why should I even care, right? So, but yeah, so without further ado, oh yeah, and finally, of course, I'd like to thank the Ethereum Foundation for kindly funding this this work. And I just press the arrow forward, I guess?
Yeah.
Okay. So, to give you an intro, as you may be aware, I think Ethereum is a chain with, by a significant margin, the highest TVL, right? 74 billion in assets. So, obviously, security, particularly in the sort of like basic infrastructure layers, is absolutely paramount in importance, right? And one of the issues is that actually the complexity of these protocols are now such that most laymen are not really able to audit the correctness of these things, right? Many people who are quite involved in the crypto community can't really tell you how the underlying consensus protocol works in Ethereum. There are lots of layers and details to it, right? And of course, now the Ethereum, Ethereum wants, and like many other chains, wants to scale to being able to be a sort of like industrial payment network style thing, right? And as you can see, there's a pretty big gap when you look at Visa's transactions per second is 4,000 versus Ethereum that can process approximately 18 transactions per second. Now, this isn't really an apples to apples comparison because the Visa transactions are just like, oh, A gives money to B, right? Whereas Ethereum transactions are like Turing complete things. It can be, in theory, arbitrary programs. So this isn't really an apples to apples comparison. Still, there are like 3 orders of magnitude of difference, so there's still a pretty big gap there, right? And in fact, there are a number of like chains that use a variety of techniques of new like novel consensus methodologies to try and radically increase it. So like I think that Solana reports a theoretical peak of 64,000 transactions per second, and they use all sorts of consensus trickery to basically be able to have people register their transactions in advance, and then the consensus kind of only happens afterwards, right? But in all of these consensus-based techniques for increasing the transaction rate, one thing remains, which is that there is still at some point a validator that needs to rerun every transaction that ends up on the chain, right? To be able to get the new state and make sure that it's valid, right? And that is a fundamental bottleneck. So how do we actually get around this? Well, the answer is, well, we don't want to actually have to check every transaction. So how do we do that? And the answer that Ethereum has come up with, and this has been really through research that has come up really since the 60s and 70s, but only really become practical in the last decade, which is this whole class of cryptographic protocols known as zero-knowledge proofs. And these zero-knowledge proofs induce these systems known as zero-knowledge virtual machines, or ZKVMs for short, right? And actually, the first time when I joined Nethermind 4 years ago, and when I first heard about these things, I actually said, no, I don't believe you. Like, it actually seems almost counterintuitive that these things exist, but they do. And we're going to talk about them a little bit today. But what they allow you to do, essentially, is they allow a machine to run some program and then produce a cryptographic proof afterwards that this program was run in some given state and then updated it to this other state, and that was done honestly without having to rerun the whole program itself. It can be done much faster than the actual original running of the program. But, and yes, and so this will allow us to switching from validators re-executing every transaction to just re-verifying these cryptographic proofs, which is much faster. Okay, so now just a quick warning. This is going to get extremely confusing because we have two kinds of proofs at play here, right? So my background actually is in logic. So I talk about, I have for me a proof is really sort of a mathematical thing where we have axioms and inference rules and we derive things from those axioms using the inference rules, right? So that's what we call a mathematical proof, and that's where my background is. And then there's a second thing, which is a cryptographic proof, which is a proof that something is true with all but negligible probability, right? Or with sometimes also known as overwhelming probability, right? So, for example, these are like cryptographic signatures and these sorts of things. Well, I can verify a cryptographic signature, and it isn't actually totally impossible that some opponent has gotten very lucky and been able to recover my private key and these sorts of things, but with very high probability, I know that I'm kind of safe. So yeah, just this sort of like warning that there's going to be lots of different kinds of proofs flying about here, so we need to keep our terms correct, or we're going to start getting confused. Yes, so we're going to give just a very quick introduction to ZKVMs. So as I said, these ZKVMs, they can produce these proofs that a program was essentially run honestly. And we call these proofs of computational integrity, right? And they're underpinned by these quite complex protocols called SNOCs. And that's an acronym. It stands for Succinct Non-Interactive Arguments of Knowledge. We're going to go through that in more detail in the next slide. And one of those protocol, an instance of a SNOC is a protocol called FRI. So there we go. We've now reached one of the words from the title, but I will maybe get to some more information about what this even is in a little bit. And there's a whole range of ZKVMs that can run multiple ISAs. These are instruction sets that your computer might understand, right? So RISC-V is very popular, but we have ZKVMs that can run the EVM directly. There's ZK MIPS, ZK WASM, and all sorts of custom ZK ISAs which are made specifically for being optimal for running in these ZKVMs, right? And so basically, if you have a program written that is compiled into any one of these computer architectures, you can actually send this to a remote computer. It can run this on, a gigantic supercomputer which can do way more compute than you could ever do locally. And it can then produce a succinctly checkable cryptographic proof that you can check, and you can know that this opponent was acted honestly without having to recheck the whole computation, which you could never hope to because it was run on a supercomputing cluster, right? So I think that's, at least for me, the first time I heard this, I almost didn't believe it, that this was possible. Okay, so now the other question. So here's another word that you might have seen in the title, which I'm going to explain. So what is lean? So as I said, my background is in logic, and so this is my world now. I'm sort of an invader almost into cryptography, if you will. But yeah, so there are these categories of things called proof assistants, and these are basically kind of like programming languages in which you can encode mathematical arguments in a form in which they are computer checkable, right? And there have been some sort of remarkable results, which I'm going to talk about in a second. But there have even been some results which have sort of actually first been verified inside of a proof assistant. Some of you might have heard of the 4-color theorem. This is the idea of like how many colors do you need to color a graph. This was actually first proven in the ROC proof assistant, because it turns out that the proof is like, they come up with this equivalence class which boils down all graphs into this gigantic set of about 100,000 different equivalence classes, and then it just needs to check one thing from each one of these. So this is a very computational proof in a sense, right? But basically this is, these theorem provers, or proof assistants rather, are software in which we can encode these sort of complex mathematical arguments, and with modern mathematics having gotten to the complexity where it is, I think it's very important to actually be able to formalize these arguments in a way that puts them under one single trust base, so that we can make sure that all mathematicians are working against this sort of like the same ground truth, if you will, right? And it's also a programming language, and this might seem a little unusual because I basically said, hey, it's kind of like a programming language, but actually it turns out that for various theoretical reasons I'm not going to get into today, it's quite difficult to make these proof assistants completely equivalent to programming languages. But actually in Lean is quite exceptional in this regard, and you can then actually write your programs in Lean and extract them and formally verify their properties. So write computer checkable arguments of the correctness of the software inside of Lean, right? And so, okay, that's all good, but why should I, or you, more importantly, I know I trust Lean, but why should you trust Lean, right? So there are a couple of things. So the first thing is actually Lean compiles everything down to a very, very simple, what we call dependent type theory. It's basically like an underlying axiomatization of mathematics, right? And it has a very, very simple kernel. The kernel establishes a shared standard of truth across all mathematics and computer science, right? Which I think is very exciting because, the truth that we pretend that as scientists, everything is objective to us. So that's a complete lie. I mean, it's not a complete lie, but it's certainly the case that if I receive, say, a paper from someone that makes a very, very strong claim, I will probably, to some extent, be deciding whether to read that or not, depending on the reputation of the person I received it from, right? That's just the truth of the matter. Whereas this actually unlocks a new dimension. I spent 2 weeks of my life going through this very terse paper. They can send me a Lean proof, I compile it, and then the Lean tells me, oh, this is true, and then I can know that it's worth investing the effort into understanding this. And this kernel that we just talked about is widely reviewed because essentially there are tens to possibly hundreds of thousands of mathematicians working with the system now who are using it every single day. So if there were ways of breaking it, it's very likely that someone would find it, including Kevin Bossert and Terence Tao, who are some of the top mathematicians of the day, are actively using this in mathematical research. It also has MathLib, which is the largest repository of mechanized proofs ever written in Lean. So all of these complex mathematical facts that we're going to need to verify things like cryptography are going to be sort of easier to be able to get because we already have all of this formalized maths. And so we propose and have been working on using Lean as a trust base for verifying all these underlying snarks that rely on very, very complex mathematical facts for their soundness, right? And particularly in the context of what is now this transition which is going to be happening over the next year with Ethereum of L1 proving, where now the L1 itself is going to be relying on the ZKVMs, right, to execute transactions. You can imagine that this is totally critical because in the worst case scenario, if these systems go wrong, we can have like state loss on Ethereum, which would be catastrophic. I can't emphasize that enough. Right? And so we want to exert the maximal effort we possibly can to try and guarantee the correctness of these systems. How am I doing time-wise, by the way? I feel like I'm doing okay. Okay, I still have time. Okay, excellent. Perfect. Okay, so now that we've gotten the sort of basics of what is Lean, what is formal verification, right? So we're trying to write proofs of the correctness of mathematical facts and software in a way that is computer checkable, right? I'm going to now quickly introduce what are these SNOCs, these magical cryptographic things that we've been talking about that underlie all of these systems, right? So as I said earlier, SNOC stands for Succinct Non-Interactive Argument of Knowledge. They're a two-party protocol where we have a party called a prover and a party called the verifier. They both agree on some relation. So this is a relation between what we call a statement and a witness. Right? And the witness is basically a secret that the prover has. And the prover and the verifier can communicate a statement between them. And the idea is that the prover wants to convince the verifier that, that he knows a witness that satisfies the relation in the statement that they both shared without actually sharing this witness with them, right? And in particular, yeah, so I always note that these are cryptographic proofs, so that once again it's with overwhelming probability rather than sort of with mathematical certainty. And so yes, so these, so that's sort of the overlying setting, but these systems have specific properties that really make them quite interesting, right? So the first one is succinctness. The verification is much faster than rechecking the full witness yourself, right? So for example, in the case of this example that I mentioned earlier, where I send some really big RISC-V computation to, you know, some supercluster somewhere, and they run this for days and days and days, they can end up with a trace which describes a computation evolving the state over time that is, you know, billions of entries, right? And that would take a very, very long time for my computer to go through and recheck, and it would be a large amount of data for the supercluster to even convey to me, right? But the succinctness means that it can be, and many of these systems work in what we call constant time. So independently of how long this computation is run for, I can check it in a bounded and relatively short amount of time that this opponent has acted honestly, which to me, once again, completely wild, right? There's the non-interactive aspect, which means is just one message from the prover to the verifier. That will become more important in the next slide. There's this argument of knowledge, right, which says, hey, the property that some of them have, which says the prover knows a witness. So there's a difference between there exists a witness and the prover actually knows the witness, must have it represented in its underlying, in the underlying computer that generated the prover, right? And the final thing is this zero knowledge, which is the verifier can't learn anything about the witness. And this can actually be quite important for some like privacy applications of these zero knowledge proofs, e.g. Aztec. Yes, and in fact, so how do we construct these SNOCs? Sorry. Well, in practice, they're constructed via the BCS transform, and we're not going to get into too much details, from these IOPs, which are interactive oracle proofs. And so this is the interactive version of these arguments, right? And yeah, as I said, we're not going to go too much into the BCS transform. I might give a very quick technical note for those in the audience who know a bit more about this. But the idea of an IOP, which is the kind of protocols from which these things are constructed, is they look like this, right? So they basically allow multiple rounds of interaction between the prover and the verifier, hence the interactive aspect, right? Where we have a commitment initially sent from the prover to the verifier, and then the verifier sends back basically just entropy, right? So it's just randomness that the prover cannot have predicted in advance. So it sends back a challenge, and then the prover needs to send back a response to that based on what this challenge is, and this will happen a bunch of times, and then right at the end the verifier will then look through all of these responses and decide whether or not he's convinced, right? And it turns out that essentially using these kinds of protocols you can encode basically anything which is what we call an NP relation. So essentially pretty much anything you can reasonably compute, you can convince someone in very, very little time that you've actually run that computation effectively. Okay, so now what are the properties that we might want to prove about such systems, right? Well, one of them is what we call completeness, right? So what the statement says here is I don't know how mathematical everyone in the audience is, but this says for all, the upside down is for all statements and for all witnesses, if the statement and the witness satisfy the relation, then, and this PR brackets means the probability of this occurring, right? Then, if I run the honest prover with the statement and this witness, and he gives me a proof, and then I run the, what is then the probability that if I run the honest verifier with the statement and that proof that it accepts, right? So basically in English, what does completeness mean? It means that if a prover has an honest witness to a statement, he's going to, with very high probability, going to be able to convince the verifier that he has a valid witness, right? And in fact, typically this epsilon c is often 0, and then we call a protocol we say a protocol is perfectly complete, right? Then the soundness, and this is the really interesting one from a cryptographic perspective. This actually says for any statement, if a witness does not exist, right? So not there exists a witness such that the relation holds, then the probability of, here the MP is a malicious proof, right? He is not necessarily running the protocol, or honestly, he might be trying to convince the verifier of something that's false. Then for any malicious prover running with the statement, the probability that the verifier will accept is very, very small, essentially, right? So that's a very important crypto. This means that proofs cannot be forged, essentially, right? So this is one of the most important cryptographic properties. And then, as we said, there's this knowledge soundness, which is a stronger version of soundness, where it's, well, not only will I not accept, but if I have accepted, then with very high probability, my prover actually knows a valid witness, right? But the actual mathematical formalization of that is quite complex, so I didn't write this down. And it's similarly for this zero knowledge, it means that, well, the even a malicious verifier cannot extract any knowledge about the witness, essentially, right? So these are the key properties that we want to be able to prove, and particularly soundness, as you can imagine, is absolutely critical to making sure that, well, if we actually have like the Ethereum L1 running using these kinds of proof systems, that we don't either lose our state or people can't exploit the cryptographic protocols underlying this, right? So this is super important, but completeness is also important for liveness, right? In the sense that if someone is doing something honest, well, they should be able to attest this to the chain, right? And so we also want completeness, but it's slightly less important because at least nothing goes really badly wrong when liveness is violated. Okay, so now I'm going to give you, and this is really a flyover, I'm going to give you a very, very quick idea of how these snarks kind of encode what a ZKVM is. So at the top level, we have a class of snarks called algebraic linking protocols. Essentially, you give them a large pile of constraints, which are just like polynomials over a mathematical object called a finite field, right? You just give them a huge pile of these things, and the algebraic linking protocol then has a prover that convinces the verifier that it knows a set of values that satisfy this constraint system without actually revealing what that set of values is, right? And if for some of the more technical people in the audience, if you start thinking, hey, is this like, can I actually encode like the full semantics of an ISO instruction set in this? Well, just realize that an actual digital circuit is actually just a polynomial constraint system over the field F2, right? For the more technical people in the audience. And so then you can encode the semantics of an ISO into these algebraic constraints. Like, for example, RISC-V, or even, like x86 or ARM, or these sorts of things that run modern computers could be in theory done. And these algebraic linking protocols rely on another kind of snark called a deep FRI. And you can see now, FRI, we've seen the word FRI again, exciting stuff, which basically proves that I have some polynomial, which I don't reveal, and I commit to it with some value in advance, and it allows me, the prover, to convince the verifier that f of a is equal to b. Right, so the verifier sends some A to you, and I can prove to him that f of a is equal to b for this f I previously committed to without actually revealing what f is at any point, right? And the final thing in this whole thing is the FRI and batch FRI protocols, which is what we've actually been working on. And this says that proving that a function that we've committed to is very close to a low degree polynomial. And the notion of low degree here is actually very, very formally defined, but we don't really have the time to go through this. I imagine I'm running quite low on time at this point. Excellent. So basically FRI is the bottom of the pile of the implementation of these ZKVMs because there are multiple sort of families of snarks which are used to implement these ZKVMs. And here we're talking specifically about this hash-based family. There are also elliptic curve-based snarks and lattice-based snarks, which I didn't expect to mention, but there was actually an expert on lattice-based cryptography in the audience unexpectedly. So I'm going to mention it. So due to that, I'm going to mention it in passing. So now that we've talked about these systems, and hopefully you have sort of an idea of how these systems, at least at a high level, work, the question is, well, what needs to be formally verified to make sure that the transition to L1 proving really doesn't go wrong under any circumstances, right? And so these are sort of the three classes of properties that we really care about here. There's a safety thing. Safety in English basically means nothing goes wrong, right? There's a category of things that we need to do for liveness. Liveness is a dual to this, which means something good eventually happens rather than just nothing goes wrong, right? And then there's privacy, which is, well, privacy is difficult to formally define, but I think in your heads you all know what that means. So to be able to guarantee safety, and this is these are a variety of things that my teams are working on, right? My team is working on. So there's verifying these constraint systems, the relationships that we feed into these things. We need to make sure that, hey, they actually correctly implement the EVM or RISC-V or all of these sorts of things. We've collaborated with Succinct and RISC-0 and a number of other ZKVMs to formally verify the constraint systems they've written down. The soundness of the underlying protocols, which we're talking about a little bit today in the next slide. So proving that FRI is actually correct and can't be tricked. And then we also want to prove the actual the implementation of the verify. So here we're working on top of like abstract models of these cryptographic protocols. But the real verifiers here are typically written in like Solidity or UL or indeed in Rust, right? The reason being that often actually you want these things to have relatively good performance, essentially. And so we actually want to then actually be formally verifying these implementations, and we have formal models. My team actually maintains the formal model of the EVM in Lean, and we also now have various teams working on formally modeling Rust. So this last one will become a very real possibility in the coming months. For liveness, we want to verify, well, as we mentioned, the completeness of the system, but also the correctness of the prover implementation. And this is going to be particularly technically challenging because the provers are very, very high performance pieces of engineering that run things on like ultra optimized GPU kernels and all of these sorts of things. So actually formally verifying that is going to be one of the most interesting challenges in this whole program. And finally, also, as I said, for privacy, we care about also like verifying the zero knowledge property, although specifically in the case of most L1s that will be participating in L1 proving, most of them don't care too much about the privacy properties for the moment. That's something for the future, and as I said, like Aztec and some other L2s which are really focusing on that aspect. And yeah, and in fact the Ethereum Foundation is running a program that is really working on every aspect that I'm writing down here. So they want to formally verify every step of, formally verify every sort of a piece of this infrastructure, because a mistake anywhere could lead to disastrous losses, right? And as I said, I really hope that as other chains also move towards using ZK technology in the primitive infrastructure layers, that they make a similar investment in doing this. Obviously, I have a bias because I get paid to do this, so of course I believe that. But yes, anyway, hopefully some of this talk has been a little technically convincing. But then, okay, so now that we've talked about this whole research project that the research that the Ethereum Foundation is funding, essentially, I'm going to give you a very quick overview of what this talk was originally kind of meant to be about, which is our work on formalizing the FRI protocol. So we actually now have fully formalized the FRI and batch FRI protocols. You can go and check this out if you go on GitHub and you search verified ZK-EVM ArkLib, Argument of Knowledge library. You will find this. I should probably have put a link up now that I think about it. But I think it's in the talk description if I remember rightly. So have a look at that. We formalize the soundness and completeness statements. And actually, oh, this is a typo. This is meant to be blueprinted, the mathematical statements, mostly in coding theory and algebraic geometry that underlie these results. So we've written the statements, but we haven't yet proven them in Lean. And we're sort of slowly working on this. So yeah, we have, this work is the first industrial scale snark which has ever been verified to this extent, right? So this is absolutely novel work. Nothing on this scale has ever been done before, and I hope I don't sound too prideful in saying this, but I'm very proud of my team for having achieved this. And we have some a paper I think coming out in Real World Crypto next year in which we're going to be describing this in detail. Okay, so now my conclusions, very quickly. basically, Ethereum relies on complex protocols, which, like complex protocols whose correctness is not really amenable to auditing by the average user anymore. So we want, and it's about to become way more complicated because of the introduction of L1 proving and SNOCs. And so we really need to basically, as I've said over and over again, try and gain the highest level of assurance of the correctness of these systems. And I hope that I've been somewhat convincing in trying to convince you that the best way to do this is by formalizing these results end to end in a computer checkable manner. Cool. Thank you for listening.